So in this lecture today, we're gonna see this if it satisfies the property of group and all kind of things. So we are gonna make table. This is our table, right? Here are the operation star. Here is the set of h, which is x4. Then here will be 4x cube, 12x square, 24x, 24, and here is 0, right? And then we make this line. You can see here. So we have this line going on. Right? And then here we have operations. 1, 2, 3, 4. 4 rows. It means we have 4 rows. 1, 2, 3, and the last one 4. 4 rows. The first operation is d naught by dx naught, then first derivative, then second derivative, then third derivative. Well, d naught x by x4, the answer is x4. It is identity, it is going to do nothing. Here also nothing. The same operator, it is identity element, so it is going to do nothing. Nothing. All will be same. Now the first derivative of this is 4x cube. First derivative of this is 12x square. First derivative of this is 24x. First derivative of this is 24. First derivative of this is 0. First derivative of 0 is 0. Now we can see here, maybe yes. So the second derivative of x4 is, well, it is 12x square. We can calculate it. Second derivative of 4x cube is, well, it is 24x. Second derivative of 12x square is 24. Second derivative of 24x is 0. Second derivative of 24 is 0, and this is also 0. Now for third derivative. Third derivative of x power 4 is 24x. Third derivative of 4x cube is so 4x cube, the third derivative, first derivative is this, second derivative is, third derivative is 24. So answer is 24. Third derivative of this is, well, first derivative is this, second derivative is this, third derivative is 0. So 0, and the all will be again 0. So we can say all these elements belong to this set H. It means it satisfies closureness. Now check this one. Check this. Does it satisfy commutativity? Well, we cannot ask this question for commutativity. You know why? Because an operator, let's say d by dx, acting on the element x power 4 is not same as x power 4 acting on d by dx, right? It's a different structure, so there is no commutativity, right? This structure does not satisfy commutativity. What about associativity? Well, let's choose A, B, C coming from set G. Well, now we have to be very careful what kind of commutativity we impose upon this kind of structure. So what kind of commutativity we associativity on this structure? Well, for commutativity, the element should, the commutativity, associativity, it should belongs to this H. Commutativity is about this set H, right? But since H cross H to H is not defined, it means all the element for all A, B, C we choose, right? It should be combination of G cross H to H, right? So we have three options. Either we have three ways. Either first A belongs to G, B belongs to H, C belongs to H. This is first way. Or AB belongs to G and C belongs to H, right? we have two ways to do this. So first is, let's say, first for this structure, so let's say A is dy dx, B is d square upon dx square, and C is let's say 4x cube. Now we have to check, is this equal to dy dx d square upon dx square of 4x cube, right? So to evaluate this, we can say dy dx, this acting on this, so the answer will be, it's a second derivative. So first derivative of this is 12x square, and second derivative will be 24x. So answer will be 24x. Evaluate further, the first derivative of 24x is 24. So we got 24 here. Now this part, well, from law of algebra, we can say this is nothing but dq by dx square, and this is acting on 4x cube. Now what is the third derivative of this? Well, first derivative of this is this one, second derivative is this, third derivative is 24. So answer is 24. So here we got 24 and here we got 24, and both are same, so it is associative, because 24 now belongs to H and this also belongs to H. So this was our assumptions, that last element should belongs to H, associativity with respect to H. Now the second option, AB belongs to G, C belongs to H, right? Or maybe we did opposite way. This one was for this set, because AB coming from G and C coming from H. Now we go for this combination. So let's say we choose the A should be coming from G and BC should be coming from H, right? So let's choose A equal to, let's choose d cube upon dx cube, okay, and let's say B equal to x square, C equal to, do we have x square in our set? Well, we do not have. So let's say choose B equal to 12x square, C equal to let's say 24x, okay, and this is our A. So we have to check A operating on B, C equal to A operating on B to C. So what is A? A is our third derivative acting on B of C. So B of C, which is 12x square acting on 24x, and it should be equal to dq by dx cube of acting on B, which is 12x square acting on C, which is 24x. Now the question is this defined? Well, we don't know what is that, right? How would we make sense of this? Because we don't know. We said O is just a composition. It's a composing on some function, right? It is not a multiplication, so we cannot multiply it. So what are we gonna do here? This is undefined. This is undefined. What about this part? Well, let's see why this is undefined. We said it because this element H cross H, this is, and H cross H is not defined in our set. We didn't say what is H cross H. We don't know. If we don't know H cross H, this does not make any sense. What about this? Well, we can calculate this one. So this will be a third derivative of 12x square. Well, what is first derivative? First derivative is 24x. What is second derivative? 24. Third derivative is 0. So we say 0 operating on 24x. So this is 0, this is operation. They are not 0. This is 0. Let me write. This and this part, if we calculate it, we got 0. Now this operation O acting on this element 24x. So what is this? This is again H cross H, and this is again not defined. You see, we don't know what this is. It means the first is failed. We cannot define this associativity with respect to this kind of rule. The associativity come from this because AB belongs to G means A cross B, right? A compose B, and this is defined because, well, G cross G is, we can do it, right? We can compose it because the function, right? I think we are making a mistake here, and that should be clarified. In all of them, we did a little tiny mistake, and the mistake was we defined this kind of things here, this, but this is not defined. Because why? Because O is defined from G cross H to H. O is not defined G cross G to G. So this is the problem. Here is G cross G. So how do we handle this? Is a little problem, and we did this mistake everywhere. Here also, see, G cross G, G cross G, G cross G. But this operation was defined from G cross H. So how do we handle this? We can handle this by just it's a small mistake. We can say, we can equip another operation, a star. So now, if we make this, then it will be defined. Otherwise, it is not. So for now, we will see this later. For now, I think these are meaningless. You see, it only satisfies closure property. Associativity is not defined because here this is defined, but here this is not defined. So one way, so it is just one way. It's just a composition happening, closure. So it only satisfies closureness, not associativity. There is no associativity in this. There is no commutativity in this. What about identity? Well, there is identity. There is identity. And what is identity? Identity should be take element from G and cross H, and we should get H. So elements from A, operation element from H should give an element some. What is identity? Identity is A cross E must be A. Now this should come from our another set, and this should come from another set, right? But is that possible? Is that possible? That is the question we are asking. So this is not possible. If I am using a star, you should make clear that this is just O, the same operation. I am just using different notation. So this is not defined because A is some operator and acting on some element. It should be element, right? So why this is not defined? Because there is no identity element here in the set H, because this is coming from H, this is coming from G. So maybe we should reverse this. This kind of identity is not defined. We could say this E star A is equal to A. This is defined. Why? Because now what is the element E with respect to A that gives A that is in set H? This A coming from G, this coming from H, right? And we can do it because E is d naught by dx naught, that is in our set. We can see here d naught by dx naught. So this is defined. So what we can say here is that we can say that for all A that is coming from H, there exists E in set G such that E operate on A gives A, right? So what is E? E will be d naught by dx naught, and we can check it. D naught by dx naught operating on any element choose from G. Let's say we had 4x cube, we had this element. The answer will be 4x cube. It is in our set. So this is one way identity. This is one way. This is one way only, not two way. In group we said EOA equal to AOE. This is equal to A, right? For example, 2 plus 0 equal to 0 plus 2 equal to 2. 0 was identity element with respect to addition. So this is true. But here it is not true. EOA does not equal to AOE. So there is identity, but only in this way. That is what we have to say this. Now, what about inverse? Then what is inverse means? So our operation O is G cross H to H. It means we take an element from A, so it will be our A, and take an element from H, B, and it should produce an element C that belongs to H, and then B will be B inverse. But again it is not defined, because A times A inverse is what? This, it means A inverse coming from H, but that is not true, because the operator of A inverse is not in set H. Operator of, this is our operator A, it is coming from G. Its inverse cannot be in the set H, it should be in the G. So maybe we can define this way: A inverse operating on A. Now that gives identity E. So what will be A inverse? Well, let's choose an element from set H, let's say 24x. So what will be here? We get E. And what is our identity? Identity is D naught by dx naught. So what should be here? That is our question. So it is not defined, because identity E belongs to set G, but here it is not defined. This does not belongs to set H, right? This belongs to set G. If it belongs to set G, then the A inverse, right? A inverse should be defined with respect to H, so with respect to G. But we said G cross H to H. We didn't say G cross H to G. So, but this says G cross H to G, but we need G cross H to H. So inverse does not exist. Okay? Inverse does not exist. Why it does not exist? Let me make it clear. Once again, we said our operation O is defined from G cross H to H, right? Now we choose, let's say our inverse is coming from this set, and an element is coming from this set, and this is acting and producing an identity. Now this identity should belong to H, but identity element is our, what is our identity element? We saw it, this one, D naught by dx naught, D naught by dx naught. But this does not belongs to H. It means inverse is not defined here, right? Even if we flip this anyway, it does not matter, right? It does not matter. It is still not defined, right? So this structure has closure, it satisfies closure, it has no associativity, it has identity, one way only, it has no inverse, and it is not commutativity. It has only closure, and identity is very restricted, but there is identity. These two property only, right? So it is satisfies closure. So what kind of structure forms this one is? So this kind of structure we call magma, because it's satisfying closure and there is identity. So we say magma with identity. Magma with identity. That's all. So this structure is magma with identity. We can expand this to make associativity, and the associativity problem was, since we were not capable of defining what this is, what this structure means, we were incapable of deciding is this even a associativity or not. So we can define this, right? But we need another operation for this, and that is more complicated. So we will maybe try to do this in next lecture.